Here we go with Chapter 9, problem number 72. Reads a 2 kilogram, 20 centimeter diameter turntable rotates at 100 revolutions per minute on frictionless bearings. Two 500-gram blocks fall from above, hit the turntable simultaneously to opposite ends of a diagonal, and stick. What is the turntable's angular speed in revolutions per minute just after this event? So I drew a little picture for looking at a face-on. Here would be our turntable, right? And here are the two blocks that are going to get dropped onto the turntable. I wrote our information that was given to us, right? 2 kilogram turntable. They said the diameter was 20 centimeters, so the radius would be 10 centimeters or 0.1 meters, always remembering to convert to meters. Here is the initial angular speed, and here is the the mass of each block. All right, so we want to know again, what is the final angular speed of our setup? All right, so we got some rotating objects, right? And what we know is that the angular momentum before the blocks hit the turntable has to be equal to the angular momentum after. All right, so if we look at what we've got here, in the beginning, the only rotating object we have is this turntable. Okay, so that is going to be the only thing we look at, and if we looked up on our chart the moment of inertia for a rotating disc, right, a spinning disc, we would find that the moment of inertia is 1/2 mr squared, and I'm going to say the mass of the turntable, right, times then omega sub I, the initial speed of it. Okay. After the blocks are dropped on there, this moment of inertia, the initial moment of inertia, becomes the sum of the moments of inertia for the three objects. Okay, so that means we have a moment of inertia for the turntable of 1/2 mr squared, right? So the m sub t r squared, and then each block is going to have its own mr squared term because we can treat them as point masses, and because there are two of them, I'm going to do 2 times mr squared, right? So the total moment of inertia is equal to the sum of the individual pieces. So here's the moment of inertia of the turntable, and then we have 2 point masses following mr squared, and then that is times omega sub f. Okay, so if we start to now go through and plug in our information, we have 1/2 times 2 times 0.1 squared times 100. And that's going to be equal to 1/2 times 2 times 0.1 squared plus 2. Each block has a mass of 0.5, and they are also 0.1 away from the axis of rotation, and then we have omega sub f. So if we crunch these numbers, right, this side of our equation becomes 1. This side, we crunch this whole big moment of inertia thing, it comes out to be 0.02, and then times omega sub f. Do a little work, right, do a little math, knock it out. We find that the new angular speed is going to be 50 revolutions per minute, which should agree with what we know about angular momentum and momentum in general, that if the moment of inertia is going to go up, right, it's going to increase, the angular speed needs to decrease or adjust so to make up for that, so that momentum is conserved, right? So it went from 100 down to 50. So there you go, there's chapter number 9, problem number 72.